In this segment of option, we are going to look at polymerization. We are only going to look at addition polymerization, which you have been used to. Of course, we are going to add more information to what you know. Polymers are also known as plastic. So here what I'm trying to do is addition polymerization of ethene, which is unsaturated, a double bond. N represent a large number, so N is simply equal to number of molecules, and I'm going to put large number of molecules, and instead of molecules we call it monomers. Those are your starting material, which is ethene. So once you have the pressure at high pressure and high temperature, these ethenes, the pi electrons are going to open up, and it's electrophilic addition, and they hold on to each other. Now what I'm showing on the other side is 1 segment, 2, 3, 4 segments of this polymer or macromolecule. It can also be shown as 1 segment, of course saturated, single bond, and N comes here to life, so you have the same amount of monomers, therefore you have a macromolecule. Now you can change the property of polyethylene by simply changing the reaction condition. We worry about that in next slide. But you have 2 possibilities. You have high density polyethylene, which are your plastic bottles, very strong. They have a high weight compared to their volume. Their melting point is high. And you also have low density polyethylene, like your SRAM wrap, and it's weaker, it's lighter, and it has low melting point. Now linear polyethylene, this here is trying to show that segment of a polymer, a large group. So this here is there, and then they are going to line up next to each other, and they will have a perfect packing going. So what it introduces weak intermolecular forces, your van der Waals, and they hold on to each other and make this extremely rigid and strong sort of a polymer. So that's high density polyethylene versus low density polyethylene. So if you change the reaction condition, now you're capable of producing branches. So if this is a backbone of one polymer, then you have other polymers attaching like this, and this branching is going to interrupt a packing, and therefore your van der Waals forces go down, your rigidity goes down, your weight goes down, and your melting point goes down. So low density polyethylene, high density polyethylene. Now the question is, how do you make them? So I'm going to the next slide, and I'm going to look at sort of the mechanism, not so much details. Definitely not high density polyethylene, although I'm going to talk about it. So this is like a supplemental. If you change the reaction condition, you can either have low density polyethylene or high density polyethylene. Low density takes place at very high pressure and high temperature, and it's a free radical mechanism, and it uses an organic peroxide as an initiator. Now on the other hand, high density polyethylene uses ionic mechanism, and it has a low pressure, 5 atm only, and it has a lower temperature, 100 degrees Celsius. And it uses a special catalyst which is made out of aluminum and titanium, sort of a complex or a mixture. Now let's just go to low density polyethylene, which you have you need to remember that it's branched, and this is what happens. A organic peroxide is just like hydrogen peroxide, except, for example, R could be CH3O attached to another CH3. So this is an organic peroxide. In initiation, it's going to produce a free radical. Now the free radical is going to attack the ethene in your pressure cooker, in your reaction vessel. So the peroxide radical is going to attack the ethene, and it's going to produce another radical, single bond dot. Now this free radical is capable of attacking other ethene in the reaction vessel. So the chain is getting bigger, but what also it can do is attack any ethene in vicinity, because its job is to go after hydrogens. So I'm going to put one more segment of this linear chain, but I want you to realize that now those free radicals can go after others. So if this is the segment of polymer, now you could also have branching going here because the free radical is attacking. Since you have branching going, you're a low density polyethylene or polyethylene, and you have properties of low melting point, you're very flexible. And if you change the pressure and temperature, if you increase them, you will have more branching going and you will have softer and softer polyethylene. Now, high density polyethylene, the mechanism is definitely not needed, but we get into it for sake of just for those of you who have questions as how it's produced. They used a catalyst made out of aluminum and titanium chlorine. It's a complex catalyst. Remember your complex ions from transition metals. It is going to do a heterolytic sort of a fusion or cleavage with your ethene, and it produces a carbocation, and the chloride is released. Then this carbocation goes after another ethene, and so forth and so on. So now you will just have a straight linear macromolecule going, and that's why it is high density polyethylene, because another branch is going to be produced like this. And remember, now van der Waals are going up, therefore your properties are changing, you become stronger, you have higher melting point. The same catalyst is also used to make isotactic, which we are going to worry about later. So in few slides you are going to see what isotactic is as a property.